Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, I'm going to look at the concept of Ampere's law, and this is going to assist us in trying to find a magnetic field of a specific part, which we are going to refer later to as, of course, a loop. Now, in this particular case, we're going to use the concept of a path integral from calculus, and this is going to assist us in trying to evaluate the magnetic field of such a kind of illustrative figure which I've given particularly for A and B, which I'm going to elaborate on later. Now in this case, we're going to consider this specific aspect or remind ourselves from the concept of a path integral, and this is going to be giving us this specific so this is going to be a reminder from our last discussion we had on various aspects of a line, a path, integral, etc. So in this case, we're going to have this arbitrarily just an illustrative figure for this one. So we are going to have this specific path having this particular element over ds. So the distance around this specific path is going to be given in terms of s, and therefore we're going to have this one given as such, and we're going to have a magnetic field, of course, which can be given in this specific case illustrated as such. Now in this case, we can find this is going to be a closed. So therefore, for this path integral, we're going to use this specific notation, which is going to be given as such, and then therefore this is going to be given in terms of the magnetic field and the d is given as such. And therefore, we are going to see that from Ampere's law, which we are going to develop later, we're going to see that for any closed loop, we can give this specific product of the, of course, the magnetic field and this specific element in terms of mu naught, and then the product of mu naught and the current, which is going to be enclosed in this specific loop. So in this case, in that summary form, therefore we are going to borrow from this specific concept of a path integral in trying to evaluate this specific aspect of Ampere's law, which is going to assist us to find this aspect of the magnetic field, which I've given in this particular case. Now that one having been said and done, then therefore we're going to start with this specific aspect of A and try to see how the analysis of A is going to assist us in trying to develop this aspect of Ampere's law. Now we're going to consider an arbitrarily closed path given using this specific form, which is going to be surrounding the current, and we're going to imagine that this particular path is made up of short segments given in terms of these specific dots. So we're going to assume that these specific dots are going to be in terms of segments, which are going to be consisting each of a length over delta L. So therefore, we're going to consider this specific arbitrarily closed path, which is going to be around the two specific current carrying conductors. And of course, they're going to be made up of short segments, which are being indicated each having a length of a delta L given as such. Now we're going to see that if we take the product of this length of each segment and try to, of course, multiply it with the components of the magnetic field parallel to that specific component. And if we sum all of this, we're going to find that the result is going to be equivalent to the product of this specific integral, which are given in terms of mu naught and the net current. Now, in this specific case, this relationship can be illustrated in terms of an equation, whereby I've said that if we take the summation over this specific magnetic field and the current element, which I've given in terms of delta L, now this is going to be given as the product of mu naught and the current, which is going to be enclosed in this specific path. Now this is going to assist us in trying to find the relationship or the representation of Ampere's law, which can be used in determining the magnetic field. And from there, of course, we're going to see that this expression, or this is going to be expressed in terms of course, the integral. Now the integral basically is going to be the summation of these specific elements given in terms of the magnetic field and of course the length of dl. So we're going to consider this specific closed path in terms of this, perhaps what we're going to refer to as an Amperean curve, and that is going to assist us in trying to evaluate the second bit given as such. So I'm going to give this specific relationship. So we're going to assume this is our equation 1. So I'm going to give this specific relationship in this specific form. whereby this is going to be equivalent to mu naught and the current enclosed in this specific case. And we're going to give this one our equation 2. So using this specific relationship, we can find the magnetic field in this particular case represented using this particular representation for equation 2, which is going to basically be culminating into the concept of Ampere's law. Now, if you consider the case for 2 which we have given, this is purely going to be one of the applications of Ampere's law, which we are going to use using this specific, of course, some section of the wire which is going to be a current carrying conductor. Now this is going to be a long straight wire, whereby we're going to see that we can construct an Amperean curve around this specific wire which we have given as such, and this specific curve is going to consist of a radius. So A is going to be the radius of this specific Amperean curve, and of course we're going to see that along this specific Amperean curve we're going to have these tangential elements, which are going to be the magnetic field components, which are going to be in terms of this, of course, tangential elements. And of course we can represent as well this one of course a magnetic field around this specific of course a loop using imaginary loop or Amperean curve using this particular formula which I've given on my of course left side of the board. That is rather. Now we can perform an integral of this specific, of course, equation in order to come up with the general representation for the magnetic field, whereby we are going to have this one given in terms. So remember from my last discussion, I had given this specific section of the arbitrary loop, which are given in terms of a ds, assuming that s was the distance around that specific loop. So we're going to have the adding up of all these elements forming the length of L. Now in this case, I'm going to consider my ds equivalent to dl. So in case I use that specific notation here, then therefore I'm going to have this specific integration given in terms of b ds, which is equivalent to the current enclosed times the of course permittivity, which I've given in terms of mu naught. So this is going to form our equation 3, whereby I've said that basically my dl is going to be equivalent to ds given as such. So from that one we can do an evaluation, whereby we're going to have this particular field as a constant, and then we shall have the integral over ds equivalent, of course, to the current enclosed times, of course, this mu. And if we try to look at this one, of course, we're going to see that for this specific Amperean curve, which is going to be circular in a form which is having a radius of 2, of course, a, the total distance around this specific, of course, Amperean curve is going to be its circumference. Now, from normal evaluation, we know that the circumference of this such a kind of a figure can be found by 2 pi r, whereby our r is going to be representing this specific radius. Therefore, we're going to have this one given in terms of u or mu current enclosed given as such. And finally, we're going to have our evaluation. Perhaps I can just give it at the top part of this specific, or rather, I can just do away with this one. Okay, just do away with this one. So we're going to have a final part of this magnetic field as the ratio between mu naught current enclosed, and then we're going to have that one divided by this specific product of 2 pi a given as such. And this is going to form a particular equation which is going to be assisting us represent what we refer to as a magnetic field. Now this is going to be application of Ampere's law, which we have said using this Amperean curve, and therefore that's one of the ways in which we can find various aspects of a magnetic field around that specific loop. Now in this case, I'd like to request our members to kindly check our description boxes for various links of other videos. Engage us in the comment section, and also subscribe and ring that notification bell to be getting updates on various uploads in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.